All right, so next up is going to be our first example of using substitution. And we're going to take this example from section 2.5, problem number 1. And it's going to be to try and solve this differential equation, x squared plus y squared dx plus x squared minus xy dy equal to 0. And so this is a differential equation in differential form. So maybe you could think about trying to rearrange it to that separable looking form. But you'd find that since you have these x squared plus y squared terms, you can't do that. Maybe you try to do like an exact equation thing. But when you take the derivative with respect to x there and with respect to y here, you get things that don't line up. And maybe you could go ahead and make this equation exact and then solve it as an exact equation. But instead, we're going to sort of look at this differential equation. And I see that there are lots of x squared and y squared. The powers are lining up here. Even this term where I don't have x squared or y squared, I have x times y, which is sort of similar to squared. So my substitution is going to be one of those proportional ones, y equals ux or x equals vy. They're the same. So I'm going to do y equals u times x. And so what I would do is I would sort of just start out by saying, if this is what I'm substituting, I'm going to go ahead and take my x squared plus y squared dx plus x squared minus xy dy, and I'm just going to plug in that substitution. So now I have x squared plus ux squared dx plus x squared minus xux dy. So that's this, like, I picked my substitution and then I plugged it in. Just like your first step of u substitution would be to sort of say what u is going to be and then make that change. But I can't remember to do the second thing, which is replace my derivatives. So I got rid of all my y's, so it's bad that I have a dy left over. So to replace my derivative, I want to change dy into something that uses du. And so you can go ahead and do this sort of by reasoning through it like a product rule. So you could say, okay, if dy is equal to, or if y is equal to u times x, then dy would be equal to u stays the same, and you take derivatives with respect to x. Or, let's see, x stays the same, and you take derivatives with respect to u. You can do that, or you could say, if it's easier for you this way, you could say dy dx is d dx of y. So that's d dx of ux. So that's just doing the same thing here. Derivative of x with respect to x is 1 times u stays the same, plus the derivative of u with respect to x is du dx, and x stays the same. And then you could say, okay, I can rearrange this as dy equals u plus x du by just sort of quote multiplying by that dx. If you're not comfortable with the differential form of taking that change of variable derivative. But now that I've found some way to replace dy in my equation, I can say, okay, that's going to give me x squared x squared plus u squared x squared dx plus x squared minus ux squared, and then replace dy with u dx plus x du, like that. And all of that should be equal to 0 because that's what my original differential equation used. And then I'm going to note that now I have this x squared term everywhere. So I can go ahead and factor that out. And I'm looking at 1 plus u squared dx plus 1 minus u times u dx plus x du. And my x squared is going to sort of cancel out because it's equal to 0. So you imagine you just divide by x squared and it goes away. And I've got my 1 plus u squared dx. And then this thing I have to multiply through. So I've got 1 minus u dx plus 1 minus u x du. So I've got 0 is equal to 1 plus u squared dx plus u minus u squared dx plus 1 minus u x du. A little more algebra to go here. So I've got my 0 equal to, where was I at there? 1 plus u squared dx. 1 plus u squared. So I had 1 plus u squared times dx plus u minus u squared, also times dx. And then times du, I had 1 minus u times x. So actually, I'm gonna keep that separate. And the reason I'm keeping it separate is because factoring can sometimes make it easier when you get to the point of solving a differential equation. So those u squared go away, and I've got 1 plus u dx plus 1 minus u x du equal to 0. And at this point, I'm just thinking about how I might possibly solve this. So my substitution is complete. And at this point, I have a new differential equation. Just ignore where it came from before. And I'm thinking maybe I can solve this as a separable equation. So I'd have u minus 1 du times x equal to 1 plus u dx. Just moved this thing over to the left-hand side, like subtracted it. And then that gives me u minus 1 over 1 plus u du is equal to dx over x. And so I can solve that as a separable equation. It's not going to be very neat, and I don't want you to sit here while I integrate that. So we're not going to solve this one all the way through. We'll just kind of like stop here and say from here, oops, solve by separation of variables. Then sort of undo the substitution. So our substitution was y equals ux. So we would use u is equal to y over x to get the solution, y equal to whatever it is. So that's our first example with using substitution to help us solve a differential equation. The next example, we'll do one that's a little bit neater to solve so that you can see the whole thing through. But this is going to go kind of slow just so you could see the general like derivative approach here.